welcome to people.
All right. All right. Good morning, good afternoon, or good evening. Welcome to the Topology Optimization webinar. Today, our session is dedicated to topology optimization for Vibro-Acoustics. It is organized by Daniele and Vanessa, both from KU Leuven. Daniele and Vanessa, thank you for organizing the session today. Please take it from here.
Yeah, so, well, Vanessa, maybe you can share the screen, yes. It's coming, so, okay, well, hello to everybody. Welcome to the 35th top webinar, which I have the pleasure to organize together with Vanessa. We are both postdocs at KU Leuven, Belgium. And the webinar of today, we have the structure that we see in the next slide. Yes. So, well, we will give an introduction to the topic, very general. Then we will have 3 presenters, and each speaker will present for about 12 minutes. And we will not take questions after each presentation, but we have reserved a slot for a Q&A session and the discussion at the end. So, well, please wait for the Q&A session to ask your question. But if you start to type them in the chat during the presentation, it's fine as well. We will just read them during the Q&A session. So, well, the question that we want to ask here is why is Vibroacoustic important and why we want to tackle it with topology optimization. So, well, in general, Vibroacoustic design is an important matter in different sectors: automotive, aerospace, construction, industry. And typically what we want to do is to, let's say, reduce the noise and vibration levels. And this relates also to an important societal challenge that we are experiencing in these days, especially excessive exposure to traffic noise has been indicated by WHO as the second largest environmental pollutant, at least in Western Europe. So typically, Vibroacoustic design for attenuation relates to increased sound insulation absorption, but also to the attenuation of structural waves. However, conventional design through, let's say, conventional, traditional, simple structural shapes makes use of significant material. And this conflicts, for example, with lightweight requirements for sustainability. So the question is, okay, can we do better with topology optimization, which typically serves the purpose of maximizing performance with the constraint on the material usage? So, well, in the next slides, I will show some of the examples along these lines of research works that popped up during the last 3 to 5 years. And here we see some examples of optimizing structures for sound insulation and radiation. In particular, we see here the thickness optimization of insulating partitions. We see that we can optimize the thickness, so the topology of the rib stiffening, to maximize sound insulation in the first 2 cases for single and double partitions, but also to minimize sound radiation when the structure is subjected to a point load. Another important focus has been on the optimization of the mechanics of resonant metamaterials, which are structures that make use of local resonators in order to create band gaps, so frequency ranges in which the propagation of structural waves is stopped. We see at the top an example of the topology optimization of these plate-like resonators, in which we want to maximize the width of the band gap. And at the bottom, we see an example in which the topology of the resonator structure is optimized to exploit multiple modes in 3D and create multiple band gaps within a certain frequency range, and also maximize broadband sound insulation. So I guess Vanessa can take it from here.
Yes, I will take over here. So in the previous slide, most of the optimizations that have been shown, it was a purely structural domain, and we are looking to some kind of vibroacoustic performance that you want to optimize. This can also be an acoustic domain, and of course, we can also go to coupled vibroacoustic topology optimization, where we have in design domain both a structural part given by the elastic equation and an acoustic part given by the Helmholtz equation. And of course, I said coupled, so there are also some coupling in between the acoustic and the structural part. And this coupling is now also present in our design domain and also will change during the different iterations. As in all topology optimization applications, there have been several formulations to solve this kind of problems. Here shown in 4 big families. The first family are the density-based methods, in which we have our gray elements. And here 2 kind of methods have been presented. The first one is a mixed displacement pressure, where we really have an interpolation between the structural and the acoustic physics. And also an element coupling contribution method, in which we we define a special element coupling matrix to have that vibroacoustic coupling into the optimization. The second family is a level set. So here we have a more discrete definition of where the coupling is happening between the structural and the acoustic parts, and we can use an Ersat material model or a remeshing technique. Then the third family is the cut-fan method, which is a kind of extended finite element technique, where we really cut the elements. So in each element that is cut, we will use some special Gaussian interpolation to make the definition of the acoustic part, the structural part, and the coupling part. And of course, we then also have the discrete variable methods, where we really have 0 and 1 variables, so that we have also a very clear definition of where the vibroacoustic coupling is happening. If we look to the literature nowadays on coupled vibroacoustic topology optimization, there seems to be 2 reference cases which are often used. So these are shown here. The top one is a transmission problem, in which the typical hourglass solution is shown, where we have our structural domain in the middle and acoustic excitation at the left, and then we want to minimize the pressure that is going through the structure at the right. The second one is a radiation problem. So this is a kind of T-shape, where we have a structural excitation at the bottom, and then we want to minimize the radiation by the structure. Of course, next to these reference cases, we can have a lot of different applications. So I'm going to show a few here. The first one could, for example, be the design of broadband filters, in which we want to enhance or minimize the transmission at certain frequencies. Then we can also look to vibroacoustic metamaterials. So the typical band gap maximization can be done for acoustic and structural waves at the same time, also including that vibroacoustic coupling. And also here in the coupled vibroacoustic topology optimization, the application of sandwich panels, or the design of sandwich panels, is often investigated, in which we look to the transmission through the sandwich panel, and we optimize it towards some sort of acoustic performance. This already brings us to the end of a very high-level introduction in topic of topology optimization for vibroacoustics. I'm going to stop sharing, and then Jonathan will be the first presenter, so he can already start setting up the presentation while I'll slightly introduce him. Okay, there's some background noise, but I'm going to try to go above that. So Jonathan Mirpourian, he's a PhD student at the Technical University of Denmark, and currently also a visiting researcher at Princeton University. And he will give us a talk on a novel interpolation for these coupled vibroacoustic topology optimization methodologies. So Jonathan, you can start sharing, and the floor is yours.
All right, can you hear me?
Yes.
Can you see my screen as well?
Yes.
All right. Okay. So first of all, thank you very much to the organizers for inviting me, and the nice introduction. I'll be talking about a novel interpolation scheme for vibroacoustics for optimization. And as Vanessa introduced nicely, I'm a PhD student from DTU, specifically Niels, who some of you might know. And I'll be talking about density-based topology optimization. And I mean, Vanessa did a very good job at introducing it. So now you're going to get a little bit more of that, and hopefully it's not too redundant for you. Okay, so let us start with a little bit of motivation. So why should you care about vibroacoustic systems? I mean, we had already some very nice introduction to that, but I just want to highlight we have them in a lot of our consumer electronics, for example, speakers or headphones. I mean, right now you probably have some kind of headphone on and you listen to me with speakers, but there's also medical applications that of course are very important, like hearing aids, which is basically a combination of speakers and headphones. And then if we want to optimize these structures, this is in general quite challenging because, I mean, they're multiphysics, and multiphysics in general means we have some kind of interface. And I mean, density-based polymerization is famous for having gray structures, so there's not really an interface. So we will now see a little bit more in depth how you tackle this during the optimization process. So if you look at vibroacoustic topology optimization, first, this is the discrete form of the equation also Vanessa showed. The structural equation and the acoustic equations. You can see at the top is an element matrix for one finite element. And the top rows, you have the solid contributions, and you have the coupling SE. And then you have in the bottom the acoustic contribution and the coupling from the acoustic to the solid. And typically, when you just normal do a finite element analysis, you have some very nice defined domains, an acoustic domain and a structural domain, and then you have some interface where you impose the coupling. Now, of course, in topology optimization, we do it a little bit different. First we mesh everything together. So now we're modeling both physics everywhere in the domain. And then we introduce now interpolation functions for all the single matrices to kind of start to distinguish between the different physics. So very broad overview, typically what you do, you interpolate them inversely. That means if you have a design variable that has value 1, you have a structural physics, and if it's 0, you have the acoustics. So you can think of all the voids as are now filled with air instead of like a very squishy material. I mean, the squishy material from the solid is still there, but now there's also acoustic physics. So with these interpolations, it's possible to recover the structural domain and the acoustic domain in this mesh of physics. And of course, then there's still some gray structure where we have a combination of both physics. Now for the coupling matrix, we need to do something special because, as I said, we don't have really interfaces in topology optimization. Here we do a closed loop integration of the coupling contributions. And now if we zoom in on a little section of our body, here we can see the discrete mesh of this body. You can see like all the lines, they represent now the coupling conditions. And because we now integrate closed loop for every single element, everywhere where there's no contrast, the contributions disappear. And this is how we kind of recover the coupling conditions only where they need to be. All right. So now let's return to a very famous benchmark. Vanessa also introduced it. It's called the acoustic partitioner problem. Here, if you look at the left, you have a wave coming in, a P in from the left side of the domain, and it travels to the right. And then you have a design domain in the middle of this problem, and you fix it at gamma D in the top and the bottom, so it cannot move the structural part. And then the objective is in the blue side, you want to minimize the pressure squared. So it's kind of the acoustic intensity or the energy of the acoustic field in that region. And you do that in an integral sense. So you could imagine if you listen with your ear in this blue domain, you don't want to basically hear anything. And then we have the classic state equation constraint, Ax equals b. We have a volume constraint. We have a classic filtering thresholding scheme with eta and beta projections, and then we have box constraints on the same level. So the rest is quite standard. So now let's see what happens if we just blindly use conventional interpolations for this problem. So here you can see the optimization history, and to the left you can see design, and then on the bottom left you can see the objective. And I mean, this doesn't look very nice. I'm sure a lot of you think maybe there's something wrong with sensitivities or something like that. And I did as well for a long time. So this is not the case. If you kind of dig a little bit deeper and you look at what you're passing to the optimizer, so that is the sensitivities of the problem. Here you can see how the sensitivities are calculated for this multiphysics problem. Here the terms 1, 2, 3, 4, and 5. So 1 is the full sensitivity of one finite element you pass to the optimizer, and 2 is the structural contribution that you pass to the optimizer. 3 and 4 are the coupling terms that contribute to the sensitivity, and 5 is the acoustic contribution. Now, if you plot these contributions, you can see that the full sensitivity for one element, 1, is basically completely dominated by the acoustics. So that is by the sensitivity equation of 5. And this is because from the acoustic point of view, if you want to block basically the wave propagating from left to right of this problem, the optimal solution is just completely make it solid. So this acoustic physics doesn't really have any knowledge of this vibrating phenomena of this vibroacoustic problem. And because the fields in the acoustic domain, when you go to the far physics realization, that means if you go to a design of 1, there's still a physical field, and it basically just blows up, and that kind of misguides our optimizer, and then we get this weird optimization history. So here's what I propose to solve this. These multiphysics interpolation functions, so called mix. Here you can see them, and I will not go into detail of that much. That's just what's important is here the Xi trans and the alpha parameter. The alpha is a steepness control, and the Xi trans is a critical transition point. Now, if you animate this, here I will show you what happens if you put alpha to a very high value and then sweep the transition point. You can see these are the interpolations. And what's important here is the transition point. And looking at to the right of the transition point, basically, if you look at the right plot, which is the derivative of the interpolation, you can see there's a zero region. So that means now it's a way with the transition point to control the sensitivity contribution, because you can kind of kill specific sensitivities. So now if you apply these sensitivities, specifically the inverse interpolation to the acoustic problem, you can get this nice optimization history. So of course there are some jumps and they are due to continuation, but you can see this is way more smooth and decreasing. And also, if you remember the objective, it was before 3, now it's roughly 2, and this is on a log 10 scale, so this is a huge improvement. And also this recovers this characteristic hourglass shape that also Vanessa talked about before. So here, just to highlight the physics, how this problem works, physically, you can see there's the wave coming from the left, and then in the middle there's this 2 arms, and basically it makes this cavity in the middle and thus decouples the wave traveling from the left to the right. Now I want to show another application of the mix formulation. Here is a flexible scalar problem. So you have 4 different finite element problems in this. P1, P2, P3, and P4. They're all different finite element problems where you have a wave coming from one side. And here the objective is to minimize the volume in the design domain. So you want to basically minimize the volume in the design domain, but keep the pressure compared to a reference pressure the same. So that means when a wave comes in and we remove material, basically the field around in the acoustic domain should not notice that we are removing material. Just to highlight one case of that, if you like, this is one of the reference cases. If you take the first wave, you can see this is how it looks like. Just to see, this is a wave coming from the left, and again we have 4 finite element problems. So there's one from the left, top, right, and bottom. And now if you optimize this, here's the volume fraction plotted with iterations, and here you can see the conventional and mixed interpolation progression. You can see that both the mixed and conventional interpolation give you a design, but again, the mixed interpolation have a very lower objective value and also converge way quicker. And this is also partly to the measure of non-discreteness. So the mixed interpolation also have a sort of built-in grayness suppression, and this helps, the measure of non-discreteness to not go so high. So you can see it's very high for the conventional interpolations, but then when it goes down, we can also boost the objective, and this doesn't happen in the mixed interpolations. And finally, I want to just kind of plot all these interpolations that I'm using right now. So you can see here a mixed interpolation, a normal one, and then inverted one. You can see a linear and a random interpolation, and you can see a transition point. And here in the gray region, you can see the mixed interpolation are basically flat. So that means you have no sensitivity contribution. So that means whatever physics you equip now with these interpolations, they basically cannot contribute in design regions from 0.8 to 1 to the sensitivity. So this is really a multiphysics interpolation, because if you have like no interpolations that have any derivative in these regions, then of course you optimize this stack. So this kind of to emphasize the multiphysics nature of these interpolations. And here you can see the physical field again from the optimization. You can see the conventional interpolation basically just carves out small kind of regions in the design, but doesn't really change much. And we have the mixed interpolation, it kind of is able to contain the pressures between these nice looking leaflets, and thus kind of stops the disturbance of the surrounding acoustic field. All right, with this, I would like to conclude my talk. So following some concluding remarks. So we identified some issues with sensitivities when we do this multiphysics topology optimization. And then we introduced this the mixed interpolation. I have to say they also act as a superset interpolation. If you choose the right hyperparameters for this interpolation, you recover again the conventional interpolation. So there's really no reason not to use them, because you can just go conventional if you want. Then some future work which would be nice in this direction is to kind of maybe come up with a coordination scheme to get these hyperparameters more automatically, and maybe also extend to other multiphysics problems. And then lastly, I would like to promote the paper. So this has been accepted in Structure and Multidisciplinary Optimization journal. And it's just right now going to the typesetting, so that takes a little while, but it should be published very soon. And to the right, you can check out my website if you want, and you will find some updates whenever I update something. Thank you very much.
All right, so thank you, Jonathan, for the very nice presentation. We can pass to the next speaker, who is Eddie Wadbro. Yeah, Eddie, feel free to share your screen. Eddie Wadbro is a professor of mathematics at Karlstad University, Sweden, and he's also visiting professor in computing science at Umeå University, Sweden. And yeah, he will talk about how we can accomplish a true wave focusing acoustic black hole through topology optimization. So yeah, please, Eddie, you can go on. Thank you.
Yeah, thank you very much. Thank you for the invite. And this is a project that I have been doing together with Martin Bergen, Linus Hög, and Abbas Musavi. And to start off, we first heard about this acoustic black hole, and were sort of a bit puzzled, like what is this type of device and how does it work? And just to give you a bit of idea on the problem descriptions, this is a phenomena that was first found in solids. And the idea here is that if you have a uniform beam and we push in a wave coming from the left towards this beam, it will go, well, to the end, and then it will bounce back. And then someone figured out the idea that if you actually do a tampering of this beam, following a power law profile, you can create a so-called ideal acoustic black hole. So when you have the wave coming from the left moving to the right, as it moves through this sort of tapered region, the apparent velocity will tend to zero. Well, and then of course the amplitude will go to infinity. But since the velocity goes to zero, this wave will never reach the end of the acoustic black hole and will thus never sort of bounce back. So what goes in always stay inside this region. From a practical perspective, the sort of tapering a beam like with down to zero does not work. So we actually will need to cut it off at some finite length. But still, since the physical properties that sound speed changes, the idea there is that they put a bit of damping material close to the end, and since the wave has sort of slowed down sufficiently much, you only need a small amount of damping material to dampen out any energy that will pop in here, because the velocity of it that it propagates to is so slow. And the design problem that we will look into, or is essentially how to design such a device that will to optimally use this small bit of damping material. And as I said, the original design and experiments for this were made for structures, so actually wave propagation in structures. But what we are interested in is standard acoustic wave propagation in air, so we only have pressure waves. And also people have looked at this from an experimental perspective and created designs, typically looking like these rib designs, and sort of arguing that by placing these ribs with sort of the decaying profile, one should get an acoustic black hole phenomenon that they will it should work in, very analogously to the structural case. And this is sort of what piqued our interest. And then we started looking into this, trying to figure out, okay, what actually happens? Because from the physical perspective, they had these devices and they did measurements and showed, whatever we put in here from this side will actually not bounce back. So they are at least fully lossy. But then we started looking into what are the damping mechanisms. And here I would just show you the sort of pressure plots for different frequencies. And what we can see here is that as frequency goes higher, it sort of looks like we get standing waves at the position that goes further and further back into this black hole. And actually what happens is that the sort of the losses are due to, well, viscothermal losses on the borders or the edges of these ribs. And they actually do not really get this nice, slowing effect so that the waves would slow and we would get a high pressure and then have some tiny bit of damping material. So the damping material actually put at the bottom does not help at all, but sort of damping comes from viscothermal losses inside the domain. So what we set out to do was to actually create a truly wave-focusing black hole where we have an input planar wave at gamma in, and we want this sort of to focus here on gamma L, so where we put the losses, or imagine you can also put like a tiny waveguide where we actually want to have all of the energy concentrated to. And then we have a design domain where we want to sort of be able to put in solid material in order to get this wave focusing effect. So this being said, so then starting off, looking at the governing equations. So we assume that we look at linear wave propagation and we search for time harmonic solutions, and then we end up at the Helmholtz equations with the following boundary conditions. So this boundary condition says that the normal derivative of the pressure is 0 on solids, essentially meaning that, well, the normal velocity is 0, so we have no velocity through this gamma s, which is at the top. The second boundary condition imposes a planar right-going wave at gamma in. That the walls, we have also, well, the same there, that the velocity is 0, and then we have some impedance boundary conditions at the lossy parts, where y here is the non-dimensional specific admittance of this lossy region. So this is the standard lossless approach. But if we now want to go in and model the losses that happens on the walls, the equations change, and in particular, not that much, only this boundary conditions on the walls change and we get two more terms that sort of take care of the viscous and thermal boundary layer themselves. So it's not, so this is the so-called Van-Zel boundary condition. So we have a PDE on the fluid domain and another PDE sort of describing, well, that sort of enters as a boundary condition here. So the sort of art here is to figure out, well, how to deal with this. But for now, I just go on, close my eyes, and say, well, if it works, it works. I will play this standard topology optimization style. So instead of computing in omega hat, which is where the fluid lives, I extend this domain to hold all domain omega, and I define a material indicator function that is 0 in the solid region and 1 in the fluid region. I put up my variational form, and this all looks fine. And two things to note here is that, well, as is standard in topology optimization, to avoid singularity, I do not really let it to be 0 in the solid, but we push some small epsilon where to sort of ensure that we have, well, a well-defined problem. And also this sort of independent looking gamma W is actually depending on the material distributions. This will depend on the design. So we have integrals depending on the design in our variational form. Nevertheless, I continue as I started by sort of not shying away, but saying, okay, now I will do finite elements on this. Again, doing this in the standard way. So I take a uniform mesh with square elements. I take element-wise biquadratic shape functions. I approximate my trial and test functions in this finite element space, and I approximate my design with an element-wise constant approximation of alpha. So far, so good. And here actually comes a very nice thing for us, because now that we have approximated our design by an element-wise constant function, we know that the only sort of interfaces between solid and fluid can occur at the faces between mesh elements. So what we do then is that we do not only have our alpha h, but we define a wall indicator eta h that sort of enters in this integrals that earlier were over the walls. But now instead we change these so that we integrate over the set of all edges in the finite element mesh in 2D or faces in 3D. And we say that, well, this one here we want to be 0 if there is no wall, or 1 if there is a wall. So now we have sort of gone from a problem where we had issues with, well, this integral over gamma w, where depending on the design, to actually having encoded this into 2 variables, alpha h describing where the material is put, and eta h describing where the walls are. And then to decide an objective, we set up a power balance. So the power that we get from our input wave will be split into the following 3 parts. So we have one that is reflected as stuff that goes in and just gets bounced back to the input boundary. The power that gets dissipated at the lossy boundary at the left. So this is the one we want to maximize. And all the power that gets dissipated and the internal walls as viscothermal losses. And yep, so we want to maximize this term here, but after having played around, we actually, well, it's equivalent to minimizing these 2, and minimizing the 2 other terms. This actually gave us a bit better performance because it apparently provides more detailed information to the optimizer to take these and separating them. So the objective, well, we want to minimize these 2 terms over a set of frequencies, and to suppress intermediate values of the design, we use a standard quadratic penalty term where this gamma here is the penalty parameter. Looking at, again, taking a step, looking at the design specification. So I let D be my unfiltered design, and then we use a morphology mimicking nonlinear filter to define our alpha H by, well, here it is, F is a filter operator, but we use the harmonic close mimicking filter, and we simply define our eta H's as the square jump between alpha on the 2 elements that are next to each face. So if alpha is 1 in both, there is no jump. If it's 0 in both, no jump. If it's 0, 1, we get a 1. If it's 1, 0, we get also 1 out. So a very simple and nice trick, sort of similar to, well, another interface detector of the sort of same style and feel as Jonathan had in his work. So what do we get from this? So starting off with showing some numerical experiments where we do optimization, not including these viscothermal losses when we do the optimization, seeing what we get. We get the design that has some small sort of, well, holes or channels, and it looks from if we just look at, okay, how does it look when we compute the performance? So the reflected wave goes down to very little, and what gets dissipated at the sort of lossy end or at the right-hand side. So it looks like we have a very nice concentration of power towards the right-hand side, which we actually wanted. But if we start to add losses or actually compute this with the linearized Navier-Stokes to check, okay, what do we really get? The performance drops a lot, and what we can see here is that the viscothermal losses inside the domain are actually really big at certain frequencies. So this sort of entails that we need to take care of these losses also in the optimization. Adding the losses into optimization, we get the design that looks much nicer. And from a perspective doing the same lossy optimization performance, we see it's not perfectly fine when it comes to concentrating the energy, but it is indeed much better. So we do have the sort of focusing effect that we wanted. So then the next thing to check is, yeah, how well does this look? So we did some animations checking it. Yeah, it sort of looks like, well, we have the focusing that we've checked, but do we actually have this sort of slowing down effect in the interior? And yep, so from animations in frequency domain, it seems like we do. But fortunately, we also got into contact with the group at TU Vienna that later on wants to build and do experiments on this. But for first, we teamed up with them, did some time domain experiments, checking, okay, what actually happens here. So long 20-meter waveguide to the left, or a very long waveguide to the left, long waveguide to the right, and then putting in a planar or a wavelet, seeing, okay, what happens when this one goes through, and looking at the wave speed in meters per second. So once this wave sort of that travels at normal ambient temperature, at normal wave speed, c, that is like 340 meters per second, when it enters, we can see this sort of waviness of the speed, but looking at the apparent velocity, it seems like it goes down over the domain, and it's clear when we're in this wave, and on the other side, the speed will go back to 340 meters per second. But inside this wave hole, like region for the black hole, the effective wave propagation speed has indeed dropped to about 230 meters per second, giving us a very nice sort of a design that both functions as a acoustic black hole, both in terms of wave focusing and in terms of slowing down the apparent velocity or the propagation velocity. And with that, I say thank you very much and happy to be here.
Yes, thank you for the very nice and interesting presentation. If there are questions, please put them in the chat and we will answer them after the third and final presentation of today, which will be given by Daniel. So you can put up your slides already. So Daniel Giraldo Guzman did his PhD in Penn State University on electrodynamic metamaterial, and he's now a postdoc at the Ohio State University and also working with a project with Honda Research Institute on cars, which also is shown in his nice background. So Daniel, the floor is yours.
It's a real background. It's not fake. The real car, what I mean. So hey, hello guys. So I'm going to present this project, which was funded by the National Science Foundation here in the United States. And this is done by many people, not just me. The project was quite extensive, and it's like a joint collaboration between the engineering design group and the ultrasonics lab at Penn State. And yeah, by any means, I want to acknowledge like all the people who work in this project. But I'm not going to present everything, obviously. I'm going to focus on the optimization part and the Vibro-Acoustics because that's what's interesting today. So before I go to the roots of the project, let me give you guys some context. Let me hide quickly this panel here for me. Okay, that was better. So this project basically has three pillars: elastic wave propagation, locally resonant metasurfaces, and topology optimization, which is the interest today, right? So I'm not sure how familiar are you guys with surface wave propagation in solids. Like most of you probably are familiar with acoustic waves in fluids. It's not very different. But this project was specifically done in surface waves and plate waves, like Rayleigh waves and Lamb waves, specifically targeting the antisymmetric A0 mode or the symmetric S0 mode. And the idea is that you can have these so-called locally resonant metasurfaces, which is just a composition of small resonators. So it's just like a bunch of resonators. They don't have a specific arrangement. They don't have to comply with periodicity, like in finite lattices. They are just like a bunch of resonant structures. And the idea is, like, if you want to prevent the propagation of this kind of waves, how do you design these individual resonators? Because depending on how you design them is the performance of your overall metasurface. So obviously we use topology optimization in this case. I probably don't have to explain what it is. I just want to mention that we use density-based, no particular reason why, it's just because we like it, because we know how to use it. And I propose like 3 different optimization frameworks, let's say, based on boundary conditions, anti-resonances, and resonance gaps. So I'm going to show you at the end a few topologies. This is like a sneak peek on how they look like. They look pretty cool, and I'm going to show you how I got to these particular shapes. So I'm going to go over like the process of creating the optimization. So just to start, the idea, and then we publish a couple of things on this, is that you can have some sort of boundary conditions that you can apply to your medium. In this case, it's a solid medium, so it's more like a displacement condition. It can apply to acoustics and fluids as well. But essentially, if you're able to apply boundary conditions to a wave propagation path, you can essentially deviate the wave or reflect the wave. As you're seeing in the animation here, you can see how much of the wave is actually not propagating through the surface. And it's similar things happen in plates, like depending on the mode you have. Either if you have the compressional mode or the flexural mode, you can apply very specific boundary conditions to the surface, and then your waves basically do not propagate. But how you apply these boundary conditions in reality, like in a real scenario. So this is what we were investigating. And we realized that the ways you impose boundary conditions, specific boundary conditions or displacement boundary conditions, is by tailoring anti-resonances. So basically, if you're able to somehow design resonators that exhibit an anti-resonance frequency or an anti-resonance at a specific frequency, you can create a bandgap. And anyone familiar with metamaterial designs knows that the bandgap is this frequency region where the waves basically do not propagate. So this is like the first abstraction. So you can impose boundary conditions just by tailoring anti-resonances, let's say. But then now the optimization problem will be like how you create those anti-resonances, how you manipulate your structure, how you do the topology optimization if you want specific anti-resonances. And the problem is simple and very complex at the same time. So anyone familiar with optimization in general or vibroacoustics problems, you already know how, what is this? This is just as since, I don't know, 20, 25, 30 years. But these eigenfrequencies usually represent resonances. And in this case, the problem is different because we are dealing with anti-resonances. For anyone not very familiar with what's the difference, resonance, anti-resonances are very sensitive to how you apply the force, where do you apply the force, what's the components of your force, the phase, and the material properties. In this case, damping is very important. So eigenfrequencies can represent resonance as well, but anti-resonances not very well. So we created like what we call anti-resonance eigenfrequencies. It's just like a modification of the problem applying boundary conditions. So the anti-resonances represent the eigenfrequencies represent the anti-resonances. But anyway, the problem is a little more complex than that. I'm going to save maybe the little details on the optimization for questions, because this is really something very general. Most of you know more or less what this diagram looks like. This is just a simple optimization loop. But I just want to highlight this little part here, which is what's most important to be able to tailor or manipulate anti-resonances is being able to recognize if an eigenfrequency, if an eigenvector is an actual anti-resonance or is just a deaf mode. A deaf mode is a mode that doesn't really exist once you have like the harmonic response. So the way we did this was like comparing frequency responses and eigenvectors to kind of search for the right anti-resonances. And once we found the anti-resonances, they correlate to eigenfrequencies. And these eigenfrequencies are just very simple to do. Like an optimization of eigenfrequencies is very simple. You already know that. But finding the anti-resonances was the real problem. So I want to show quickly some results. This is like very high level. And basically what we found is some sort of correlation between the anti-resonance and the frequency bandgaps. So once you have the metasurface in place, you can correlate the anti-resonance frequency with more or less the lowest point of your frequency bandgap. And what you're seeing here in this plot is just a transmission plot that we created. Like the way we compute transmissions is very unique. But anyway, we just want to highlight here in the red line that you have a lot of transmission loss, and the frequency sort of correlate with the anti-resonances of the frequency response. So this is just like both numerical and experimental proof that we have something going on, and I have more results to show. But then what's most interesting in reality is how you generate this kind of resonators for surface waves. So basically, the surface waves, for those of you that are not aware, the particle motion is elliptical. So it goes up and down and back and forth. So you have to design your topology optimized resonator for both the in-plane motion and the out-of-plane motion. So you are constraining basically two components of the surface wave motion. And the way you generate a band gap for this particular problem is tailoring anti-resonances for both motion components in the frequency range that you're interested. So in this case, I created this resonator that it looks like a turkey in reality, but what's interesting is that you can tailor two different anti-resonances subject to two different motion components. And when you put together a lot of these resonators in a metasurface, you can actually generate a band gap and prevent the propagation of waves. So in this animation, you are just looking at half of the metasurface. I cut the metasurface by half, so you can see inside the space what's happening with the waves underneath the metasurface, so you can see some sort of deviation. And we did this experimentally, like numerically and experimentally. We have excellent agreement. And basically, we kind of found that if you are able to control multiple motion components and multiple anti-resonances, you can generate not only better band gaps, but wider band gaps. And then obviously the question later was like, well, can we make it wider? So yes, we can make it wider. And now the optimization problem is just like a combination of the previous anti-resonance matching. And now we are taking all the resonances and pushing them as far as possible from the anti-resonance, so we can generate like a frequency band gap that is just very wide. That's the basic idea. Again, optimization-wise, this is somehow simple. Physics-wise, physics-wise, it's not that simple, but it works. So in this case, I'm going to show you just like a couple of examples, in this case for plate waves, because the plate wave problem is very challenging in terms of getting wide band gaps. And this is something that we actually published like 2 or 3 weeks ago. And basically it's the same principle. So you have an anti-resonance that you are tailoring at a specific frequency where you want to generate the band gap. But in addition to that, you are pushing the resonances so far away that your band gap could be very, very wide. And it works. So this is like a reference metasurface that we have. It's just like a bunch of prismatic rectangles. It's just like prismatic rods. So there is nothing optimized for them except for the frequency that they were supposed to generate the band gap. And then we have the very first topology that I show you, which looks like an elephant, because the trunk is moving up and down. And the band gap in this case was very narrow, even worse than the prismatic resonators, which is not optimized at all. But then when you introduce both anti-resonance matching and resonance gap enhancement, now you have like a super wide region where basically your waves do not propagate. And this is great. So I just wanted to like finish highlighting that probably the biggest contribution here is being able to have a super efficient and super simple optimization based on eigenfrequency matching or eigenfrequency manipulation, which is very simple, but powerful enough if you compute frequency responses and you are able to find the right eigenfrequencies in the right frequency range. And then obviously numerical and experimental results are very important and they correlate perfectly. So we are very happy for that. So that was very quick. It's just like a high level introduction. I know there are many nuances and many little details about the optimization that I didn't mention, but just feel free to ask. That's it.
All right. So, well, thank you very much, Daniel, for the presentation. Very nice. And well, we can open the floor for questions. So if you have a question, I see that there are already some questions in the chat, but feel also free to unmute yourself and speak up.
No. Maybe I can start. I can see some chat questions.
Yeah, please go ahead.
I will read the question that everyone who is also following on YouTube can follow. So the first question is, in the frequency range analyzed, the author believed that there are no local acoustic resonances in the final configuration. So he's wondering, is that correct? And in the case of larger fluid medium where acoustic resonances do occur, do you think there could be issues in the acoustic part of the sensitivity analysis, similar to what happens in the structural part?
So if I understand this correctly, so I believe there's no acoustic resonance in the final conversion. I haven't checked that explicitly. So I mean, typically, I believe what you do is you choose your interpolation parameters. So you kind of try to push away unwanted resonances in your acoustic domain. So I think the issue really here with the sensitivity analysis is that in acoustics, we do this inverse interpolations. And when we have like something that is non-physical, that means we have like a solid kind of, actually there's a physical field of the acoustics, which is like potentially infinitely large. Because if you think about standard density-based for solids, you have like kind of very solid structure, and then you have like kind of marshmallows, which deforms a lot. So there's some physical sense in that. But in acoustics, it's like, there should be no field actually in the solid, but there is, because we're using a density-based polymerization. So the field blows up to infinity. So I think the thing is that the physics itself, the way we interpolate the acoustics, is actually kind of the issue when we do vibroacoustics optimization. So I mean, definitely, I think for your problems you need to check that. And yeah, I hope that answers the question roughly. Maybe Vanessa, another question maybe, or maybe someone else. I don't want to take all the spotlight.
Yeah, there was another question in the chat for Jonathan. So the final topology using your interpolation, it was slide 12, gives almost a different result with respect to the common methods. Could the optimal design cause issues in the connectivity of the cells? And what about the final values of the objective function?
Yeah, so if I understand common methods correctly, I'm assuming the common interpolations. And the connectivity of the cells, I mean, there's no connectivity constraint in this, so there are some floating islands, and definitely they will change the final objective value. I cannot tell you if it would go up or down. Probably will go, I mean, it would get worse if you impose connectivity, but I haven't tried that. Yeah, I hope that answers the question. If not, please let me know.
All right, so let's see if we have more questions. Well, in the meanwhile, maybe I will ask one to Eddie. So, well, in your design problem, you have kind of concentrated losses at the end of the domain on the in the right part. So I was wondering, like, how are these concentrated losses, let's say, tuned, and if your design would change if you change those concentrated losses, and well, if you can see it as a further design parameter, or well, if you can comment on that.
So let's see, I will just quickly put up the problem description. So I guess that you're asking about the losses here at this end, right?
Yep.
So this is, well, what we tried to do was to do a problem, or a problem that as close as possible mimics the original, or the sun, or the acoustic black holes for beams, where the solution they used was to simply put, for beams it's easier. You have this tapering, and you need to cut it off, and you put a small amount of damping material. So our idea here was that, well, we want to do something similar. So we have a certain length of the design domain, and what we want to do is to concentrate the acoustic energy that comes in to this small part here, where we actually have damping material that eats up whatever, acoustic energy that comes in. So it's sort of like a low-cost damping, so that you would minimize the use of damping material. So this is why we put that one here. But of course, you can likely tinker with sizes and see, okay, well, what should be put there.
Yeah, all right, thanks.
And I stop share again.
I would have a question to Eddie as well.
Yep.
So actually, it's one question and I hide free in them. So first question, Eddie. So the discretization, like the discretization size, how sensitive is your optimization to like the mesh size?
Not very much. Well, the discretization size is more, well, as in many cases with the poly optimization, you do a ridiculously fine discretization because that, well, by some magic, if you have a finer discretization, you get nicer looking designs. They get sort of smoother and work better. But then I haven't noticed any size effects on the discretization. So here and also it's much finer than what you would need to actually resolve the wave propagation. So the wave propagation is extremely well resolved at the discretization size we're using.
Okay, thank you very much. I guess for the post-processing, it's quite important, right, that you have a high discretization, right, when you compare to the linearized Navier-Stokes.
Yep, and we've also tried this, both with, well, pushing in the staircase design as well as a smoothened one, and both of them are very close in performance. So there, I actually think that we benefit from that. That sort of the acoustic problem is over resolved, so to say, and that, well, sort of the staircasing that effectively makes something larger, but when you smooth this out, you get the normal in a sort of more better aligned with what you would have normally. So these things, yeah, again, by magic cancel out, and the results do not sort of deviate too much.
All right, and then maybe just a open question: would you think the design would change a lot if you add the vibrations, like the solid vibroacoustic?
It could potentially change quite a bit, and it would be cool to sort of try to move over and try to use this sort of method for, well, additional problems. Now, what I have not pushed to, well, vibroacoustics or multiphysics problems yet, but I would love to check if it works.
All right. Thank you so much for the answer.
Thanks.
Okay, so, well, maybe I will ask a question also to Daniel, since he didn't get questions yet. So if I understand correctly, you optimize your resonator, and you focus only on the resonator design, and you want to tune anti-resonance frequencies and so forth. I was just wondering what kind of boundary conditions and applied loads, if any, you used for the to compute these anti-resonance frequencies, and how the problem is exactly set up.
Let me see if I understood your question. So in terms of, you say, what boundary conditions to get the anti-resonances?
Yes, exactly, because I would assume that the anti-resonances and stuff would depend on the boundary conditions that you applied. So I was wondering if, I don't know, if you fix the base of the resonator and attachment with the whole structure, or if you do something else, it's free conditions. I was just wondering that.
No. So basically, we are using displacement constraints in the direction where you want to see the anti-resonance. And let's say you want to see multiple anti-resonances, then you have to compute multiple eigenfrequency problems with different boundary conditions, because the anti-resonances are hard to catch sometimes, so you have to separate them and run individual tests. But they are just displacement constraints in the degrees of freedom where you want to see the anti-resonance, and at the location where you want to see the anti-resonance. And it's very sensitive to the area. If you want like a very large area, it doesn't work that well. It has to be relatively small.
Yeah, all right, thanks. I don't see any other question.
Sorry to interrupt. I'm about to leave. So if someone has questions for me, then please give me them now. Else, I think very soon.
Yeah, all right. So we don't have any more questions.
Seems to fit perfect with the time spans. We are at the end of the session. Yeah. Great. Thank you for a very interesting talk. Jun, do you have something to say about the next?
The next, okay. we really don't have planned for sessions in March and April. I guess we will see each other in WCSMO in Japan in May. So thank you, Vanessa and Daniele, for organizing this session, and thanks to all the speakers for joining us, and also the audience. Thanks. See you in Japan or in another session in September. Yeah.
We hope to see many of you there.
Bye.